Look up at the night sky on a clear winter evening, and you will find Orion the hunter striding across the heavens. His belt of 3 bright stars points the way, and there, marking his right shoulder, burns a star unlike any other. Betelgeuse, a crimson jewel suspended in the darkness. For thousands of years, humans have gazed upon this red beacon and wondered about its nature. But in late 2019, something strange happened, something that made astronomers around the world sit up and take notice. Betelgeuse began to fade. The bright shoulder of Orion was dimming before our very eyes, and nobody knew exactly why. Welcome to Cosmic Drift, where we explore the wonders of the universe in a way that helps you relax and drift off to sleep. If you enjoy this kind of soothing science content, please take a moment to like this video and subscribe to join our sleepy science community. Now, let us settle in and discover the fascinating truth behind one of the greatest stellar mysteries of our time. Betelgeuse is not just any star. It is a red supergiant, one of the largest and most luminous stars visible to the naked eye. If you placed Betelgeuse where our sun sits at the center of our solar system, its outer edges would extend past the orbit of Mars, perhaps even reaching as far as Jupiter. Try to picture that for a moment. A star so enormous that it would swallow Mercury, Venus, Earth, and Mars whole, with room to spare. This is the scale we are dealing with when we talk about Betelgeuse. The star sits roughly 650 light-years away from Earth. That means the light we see tonight actually left Betelgeuse around the year 1375, during the height of the medieval period on Earth. When that light began its journey across the cosmos, the Black Death was still fresh in the memories of Europeans, and the Renaissance was just beginning to stir in Italy. Such is the nature of starlight. It carries ancient messages across unimaginable distances, arriving at our eyes as a whisper from the distant past. For most of human history, Betelgeuse appeared as a steady, reliable presence in the constellation of Orion. Ancient cultures gave it many names. The Arabic name from which we derive Betelgeuse likely meant something close to the hand of Orion, or the armpit of the central one. Yes, some scholars believe it refers to an armpit. The Egyptians associated the star with Osiris, god of the afterlife. Indigenous Australians saw Betelgeuse as part of their own rich constellation stories, passed down through countless generations. But despite this long history of observation, we have only recently come to understand what Betelgeuse truly is. And even more recently, we witnessed something that challenged everything we thought we knew about this cosmic giant. In the autumn of 2019, astronomers began noticing that Betelgeuse was getting dimmer. At first, this did not seem too unusual. Betelgeuse is what we call a semi-regular variable star. This means its brightness naturally fluctuates over time. The star breathes, in a sense. It expands and contracts, and as it does so, its brightness rises and falls in cycles. Astronomers have tracked these cycles for over a century, identifying periods of roughly 400 days and around 5.9 years that govern the pulsations. So, when Betelgeuse started to dim in late 2019, some observers simply noted it as part of the normal cycle. But then the dimming continued and continued. By February of 2020, Betelgeuse had faded to just 36% of its normal brightness. This was unprecedented. In all the decades of careful measurement, nobody had ever recorded Betelgeuse this faint. The star that had always been among the 10 brightest in the night sky had slipped to around the 23rd position. For anyone familiar with Orion, the change was visible to the naked eye. The constellation looked lopsided. Betelgeuse, which should have balanced the blue-white brilliance of Rigel on the opposite corner, now seemed almost to cower in the darkness. The astronomical community erupted with speculation. Headlines around the world asked the same breathless question. Was Betelgeuse about to explode? You see, Betelgeuse is a star living on borrowed time. Red supergiants like Betelgeuse represent the final life stage of massive stars before they meet their ultimate fate as supernovae. These are not gentle, quiet deaths. A supernova is one of the most violent events in the entire universe, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. When Betelgeuse eventually explodes, and it will explode, the event will be visible from Earth, even in broad daylight. For weeks, perhaps months, a new star will blaze in our sky, bright enough to cast shadows at night and visible as a distinct point of light during the day. So you can understand why astronomers grew excited when Betelgeuse began its mysterious dimming. Could this be the sign that the explosion was imminent? Was humanity about to witness one of the rarest and most spectacular events in astronomy? To answer this question, we need to understand more about how red supergiants work and what happens in the final stages of their lives. So let us take a journey deep into the heart of Betelgeuse and explore the forces that shape these magnificent cosmic giants. Every star, including our own Sun, is essentially a careful balancing act between two opposing forces. On one side, you have gravity. Gravity is relentless. It pulls everything inward, squeezing the star, trying to compress all that material into the smallest possible space. On the other side, you have the outward pressure created by nuclear fusion in the star's core. This fusion pressure pushes outward, resisting gravity's constant inward pull. As long as these two forces remain in balance, the star remains stable. For most of a star's life, this balance works beautifully. Our Sun has maintained this equilibrium for about 4.6 billion years, and will continue to do so for another 5 billion years or so. The Sun fuses hydrogen into helium in its core, and the energy released by this process creates enough outward pressure to perfectly counterbalance gravity's squeeze. But Betelgeuse is not like our Sun. Betelgeuse started its life as a much more massive star, perhaps around 15 to 20 times the mass of the Sun. This extra mass changes everything. More massive stars burn hotter and faster than smaller ones. While our Sun will shine steadily for about 10 billion years, a star like Betelgeuse races through its fuel supply in a cosmic blink, perhaps just 10 million years from birth to death. That might sound like a long time to us, but remember, the universe is nearly 14 billion years old. In cosmic terms, Betelgeuse is like a brilliant candle that burns brightly but briefly. Because Betelgeuse has already consumed so much of its fuel, it has moved far beyond the simple hydrogen to helium fusion that powers younger stars. When a massive star runs low on hydrogen in its core, it does not simply fade away. Instead, the core contracts under gravity's relentless pressure, heating up until it becomes hot enough to fuse helium into heavier elements like carbon and oxygen. When the helium runs out, the core contracts again, heating further until it can fuse carbon, then oxygen, then silicon. Each new fuel source provides less energy and is exhausted more quickly than the last. Meanwhile, as all this drama unfolds in the core, the outer layers of the star respond in dramatic fashion. The energy pouring outward from the core's increasingly desperate fusion reactions causes these outer layers to expand enormously. The star bloats, swelling to hundreds of times its original size. At the same time, as the outer layers spread across such a vast volume, they cool down. The surface temperature drops from the blue-white heat of a young, massive star to the cooler red hues of an aging giant. This is how Betelgeuse became a red supergiant. It is not fading out of existence, but rather expanding through its final life stages. Inside Betelgeuse today, the internal structure resembles something like a cosmic onion. Layer after layer of different elements surrounds a core that is growing ever denser and hotter. The outermost layers still contain hydrogen and helium. Deeper in, fine shells of carbon, then oxygen, then neon, then silicon. At the very center, an iron core is slowly building up, atom by atom, and this iron core is the key to understanding Betelgeuse's ultimate fate. Iron is different from all the lighter elements that stars can fuse. When you fuse hydrogen into helium, you release energy. When you fuse helium into carbon, you release energy. The same is true for oxygen, neon, and silicon. But iron is the end of the line. Fusing iron does not release energy. Instead, it requires energy. This means that once a star has built up a large enough iron core, the game is essentially over. No more fusion can save it from gravity's final victory. When the iron core reaches a critical mass, roughly 1.4 times the mass of our entire Sun packed into a sphere smaller than the Earth, something catastrophic happens. The core collapses in on itself at speeds approaching 1/4 the speed of light. In less than a second, the core shrinks from a ball the size of Earth to a dense sphere just a few miles across. This sudden collapse sends a shockwave tearing outward through the star's remaining layers, and the result is a supernova. But here is the thing. All of this happens deep inside the star, hidden from our view. The core collapse and the initial stages of the explosion occur behind hundreds of thousands of miles of stellar material. By the time any sign of the supernova reaches the surface and becomes visible to astronomers on Earth, the core has already completed its dramatic transformation. So even though astronomers know that Betelgeuse will someday explode, predicting exactly when is extraordinarily difficult, the relevant processes occur in regions we cannot directly observe. This brings us back to the great dimming of 2019 and 2020. When Betelgeuse started fading, astronomers had to consider all the possibilities. Was this dimming a sign that something dramatic was happening in the star's core? Were we witnessing the beginning of the end? The short answer is no, but the longer answer is far more interesting, because what actually caused the dimming turns out to be a fascinating story about how red supergiants behave and how the surface of a star like Betelgeuse is nothing like the relatively calm surface of our Sun. To understand what really happened, we need to talk about something called convection. You are probably familiar with convection from everyday life, even if you do not know the term. When you heat a pot of water on the stove, you can watch convection in action. The water at the bottom of the pot, closest to the heat source, gets hot and expands. This makes it less dense than the cooler water above it, so it rises. As it rises, it cools, becoming denser, and eventually sinks back down. This creates a continuous cycle of rising and falling that you can see as the rolling motion of boiling water. The same basic process happens inside stars, but on an almost incomprehensible scale. In our Sun, convection occurs in the outer layer, where massive cells of hot plasma rise to the surface, radiate their heat into space, and then sink back down into the interior. These convection cells are about 1,000 kilometers across, which sounds enormous until you remember that the Sun itself is nearly 1.4 million kilometers in diameter. On the Sun, thousands of these cells cover the surface like a carpet of churning bubbles. But Betelgeuse is different. Remember, Betelgeuse is vastly larger than the Sun. Its convection cells are correspondingly huge. Instead of thousands of small bubbles, the surface of Betelgeuse features just a handful of enormous convection cells, each one large enough to swallow planets. When one of these giant cells rises to the surface, it can cause a visible bright spot. When it sinks, the surface darkens. The entire star seems to bubble and roil in slow motion, with features rising and falling over periods of weeks or months. This giant-scale convection has consequences that extend beyond the visible surface. The powerful upwelling motions can push material outward into space. Hot gas rises from deep within the star, carrying with it dust and other materials that get ejected into the space surrounding Betelgeuse. Over time, this process has created an enormous envelope of gas and dust that surrounds the star, detectable by telescopes sensitive to infrared light. In the years leading up to the Great Dimming, something unusual happened. One of these massive convection cells created an exceptionally powerful upwelling. A huge bubble of hot gas rose toward the surface of Betelgeuse, carrying with it an enormous amount of material. When this bubble reached the surface, it did not simply cool and sink back down like normal. Instead, the material was ejected outward, away from the star entirely. Astronomers now call this event a surface mass ejection, and it was truly massive. Imagine taking a chunk of the Sun's surface and flinging it into space. Now multiply that by a factor of several hundred. The amount of material Betelgeuse expelled during this event was staggering, perhaps 400 billion times the mass of a typical solar coronal mass ejection from our own Sun. This enormous plume of hot gas flew outward from Betelgeuse at tremendous speed. But as it traveled away from the star, it began to cool. And as it cooled, something important happened. The gas contained various elements, including silicon, oxygen, carbon, and metals. At high temperatures, these elements exist as individual atoms or ions, bouncing around freely. But when the temperature dropped below a certain threshold, the atoms began to combine and solidify into tiny particles, dust. The cooling plume became a cloud of dust, drifting in the space between Betelgeuse and Earth. And this dust cloud had one very important property. It blocked light. Think about a cloudy day on Earth. The sun is still there, burning just as brightly as ever. But the clouds block some of its light, making the day seem dimmer. The same thing happened with Betelgeuse. The star itself had not significantly changed. Its nuclear fires still burned. Its surface still radiated light across the electromagnetic spectrum. But a massive cloud of dust now sat between us and the star, absorbing and scattering a significant fraction of that light before it could reach our telescopes. This is what caused the Great Dimming. Betelgeuse sneezed, and the resulting dust cloud gave us all a fright. The evidence for this explanation came from multiple sources. The Hubble Space Telescope captured images of Betelgeuse before, during, and after the dimming event. These images showed clear changes in the distribution of brightness across the star's visible surface. Before the dimming, Betelgeuse appeared relatively uniform, with the normal mottling caused by its giant convection cells. During the dimming, the southern hemisphere of the star appeared dramatically darker than the northern hemisphere. This asymmetric darkening was exactly what you would expect if a dust cloud was blocking part of our view. Other telescopes contributed their own pieces to the puzzle. The Very Large Telescope in Chile used specialized instruments to study the dust around Betelgeuse. These observations revealed the presence of newly formed dust particles in the region where the surface mass ejection had occurred. The timing matched perfectly. The dust had formed at exactly the right time, and in exactly the right place to explain the dimming. Spectroscopic studies provided additional confirmation. By analyzing the specific wavelengths of light coming from Betelgeuse, astronomers could determine the temperature and chemical composition of the material around the star. These studies showed that the dimming was most pronounced at visible wavelengths, while infrared observations showed less dramatic changes. This pattern is characteristic of dust absorption. Dust particles preferentially block shorter wavelengths of light, like visible blue and green, while letting longer wavelengths like infrared pass through more easily. Everything pointed to the same conclusion. Betelgeuse had expelled an enormous cloud of material from its surface, and this material had cooled and condensed into dust that temporarily blocked our view. The great dimming was not a sign of imminent supernova. It was a stellar sneeze. But that raises an interesting question. If Betelgeuse just experienced a particularly dramatic version of a normal process, why had astronomers never seen anything quite like this before? The answer lies in the coincidental timing of several factors coming together at once. Remember those pulsation cycles we mentioned earlier? Betelgeuse has multiple overlapping cycles of expansion and contraction. The main cycle lasts about 400 days, while a longer cycle takes about 5.9 years to complete. When these cycles align in certain ways, they can reinforce each other, creating conditions for particularly dramatic events. In late 2019, both cycles were approaching phases that made the star's outer layers particularly unstable. The shorter cycle was causing the star to contract, while the longer cycle was also trending toward a minimum state. This double dip created conditions where material ejected from the surface was more likely to travel outward rather than fall back. It also meant that even after the dust cleared, Betelgeuse would appear dimmer than normal, simply because both pulsation cycles were at low points simultaneously. The surface mass ejection happened at exactly the wrong time, when these pulsation cycles had already made Betelgeuse appear relatively faint. The dust cloud made things dramatically worse. The combination of factors produced a dimming event far more extreme than any single cause could have created alone. This explanation also helps us understand why Betelgeuse has been behaving somewhat strangely ever since. The surface mass ejection removed a significant amount of material from the star's outer layers. This is not a trivial thing. Red supergiants like Betelgeuse are only loosely bound by gravity in their outer regions. The material in the outer layers is held tenuously, and removing a large chunk of it can disrupt the delicate balance of the entire star. In the years since the Great Dimming, astronomers have noticed that Betelgeuse's pulsation behavior has changed. The regular cycles that had been observed for decades seem to have been disrupted. The star is still pulsating, but the timing and amplitude of the pulsations have shifted. It is as if Betelgeuse is still recovering from its cosmic sneeze, trying to settle back into its normal rhythm after the disruption. Some researchers have described this as Betelgeuse having the stellar equivalent of hiccups. The star is adjusting to the loss of material, and its internal dynamics are temporarily out of balance. Eventually, Betelgeuse will likely settle back into a more regular pattern, but that process could take years or even decades. This ongoing recovery provides astronomers with a unique opportunity. By watching how Betelgeuse returns to normal, we can learn enormous amounts about the internal structure and dynamics of red supergiants. These stars are difficult to study because they are so rare and so far away. Having one undergo a dramatic event and then recover, all while we have modern telescopes trained on it, is like having a front row seat to a cosmic laboratory experiment. The Hubble Space Telescope has continued to monitor Betelgeuse capturing images and spectra that document the recovery process. Ground-based observatories around the world have joined the effort, contributing data across multiple wavelengths of light. Radio telescopes have mapped the distribution of molecules in the expanding cloud of material ejected during the surface mass ejection. All of this data is helping astronomers build a more complete picture of what happens when a red supergiant loses its composure. One particularly fascinating aspect of this research involves the dust itself. The particles that formed in the cooling plume are not just random clumps of matter. They are complex, intricate structures that form through chemical processes we are only beginning to understand. These dust particles are the building blocks of planets, asteroids, and eventually, life itself. Every atom of carbon in your body, every grain of silicon in the sand on a beach, every trace of iron in your blood, all of these elements were forged in the hearts of stars and scattered into space by events like the one we witnessed at Betelgeuse. When Betelgeuse eventually explodes as a supernova, it will release its accumulated material into the galaxy. The dust cloud that caused the Great Dimming is just a tiny preview of what is to come. The final explosion will scatter elements across hundreds of light years, seeding space with the raw materials needed for new stars, new planets, and perhaps new life. But let us return to the question that sparked so much public interest in 2019 and 2020. If the Great Dimming was not a sign of imminent supernova, when will Betelgeuse actually explode? The honest answer is that we do not know. Estimates range widely, from a few thousand years to perhaps 100,000 years or more. That might sound like an unsatisfyingly vague answer, but it reflects the genuine uncertainty in our understanding of stellar evolution at these final stages. Here is the challenge. The processes that determine exactly when a massive star will explode happen deep in the core, where we cannot directly observe them. The iron core at the center of Betelgeuse is growing slowly but steadily as silicon fusion continues in the surrounding shell. When that core reaches the critical mass, the collapse will happen suddenly and without warning. There are no known external signs that reliably indicate a supernova is imminent. A star could appear perfectly normal one day and explode the next. Some astronomers have searched for subtle clues that might hint at an approaching supernova. One idea involves studying neutrinos, ghostly particles produced in enormous numbers during core collapse. In theory, neutrinos from a collapsing star would reach Earth hours or even days before the visible light of the explosion. Neutrino detectors around the world are always watching for this signal. If Betelgeuse's core begins to collapse, we might receive a warning in the form of a sudden burst of neutrinos. Another approach involves looking for changes in the star's pulsation behavior that might indicate instabilities in the core. The Great Dimming has actually complicated this effort somewhat, because it disrupted the baseline pulsation patterns that astronomers use for comparison. It will take time to establish what normal looks like for post-dimming Betelgeuse before we can identify any truly anomalous behavior. Despite these uncertainties, we can make some confident statements about what will happen when Betelgeuse does explode. The event will be spectacular. Betelgeuse is close enough that the supernova will reach an apparent brightness roughly matching the full moon. For weeks, this new star will dominate the night sky, outshining every other celestial object except the sun and moon themselves. Daylight observers might catch glimpses of it, a strange new point of light visible even against the blue daytime sky. The explosion will also provide humanity with an unprecedented scientific opportunity. Modern telescopes across every wavelength of light will capture data from the event. Neutrino detectors will will measure the particle burst from the collapsing core. Gravitational wave observatories might detect ripples in spacetime itself. For astronomers, a nearby supernova would be the scientific event of many lifetimes. But should we worry? Is there any danger to Earth from a Betelgeuse supernova? The short answer is no. Betelgeuse is far enough away that the explosion poses no threat to our planet. A supernova releases deadly radiation, including intense gamma rays and X-rays, along with charged particles and shock waves that can sterilize nearby solar systems. But these dangerous effects diminish rapidly with distance. At 650 light-years away, Betelgeuse is comfortably beyond the danger zone. The increased radiation reaching Earth would be detectable, but not harmful. Astronauts in space might receive a slightly elevated radiation dose for a few months, but nothing serious enough to pose health risks. There has been some speculation about whether a supernova could damage Earth's ozone layer, allowing harmful ultraviolet radiation from the Sun to reach the surface. Studies suggest that this would only be a concern for supernovae within about 50 light-years. Betelgeuse is more than 10 times that distance. We can enjoy the cosmic fireworks without fear. What will the supernova look like from Earth? Let us paint a picture. Imagine a clear winter night sometime in the future. You step outside, perhaps on a walk, or simply to gaze at the stars as you do from time to time. You look up at Orion, that familiar hunter in the sky, and immediately notice that something is different. Where Betelgeuse once glowed a faint red, there now blazes a brilliant white-blue point of intense light. It is so bright that it hurts to look at directly. The entire constellation seems unbalanced, overwhelmed by this newcomer that outshines all its neighbors by 100 times. Over the following nights, the new star slowly fades, transitioning through yellow and orange hues as the initial explosion gives way to the expanding cloud of debris. Within a few weeks, it dims to the point where it no longer dominates the sky, though it remains easily visible to the naked eye. Months pass, and the point of light continues to fade. After perhaps a year, it has dimmed below naked eye visibility, leaving behind an expanding cloud of gas and dust that will remain visible to telescopes for thousands of years. This expanding cloud is called a supernova remnant, and it represents the final chapter of Betelgeuse's story. The material ejected by the explosion will spread outward into interstellar space, eventually mixing with the gas and dust that pervades our galaxy. Over millions of years, this enriched material will be swept up into new collapsing clouds, forming new stars and new planetary systems. The elements forged in Betelgeuse's core and scattered by its death will become part of new worlds, perhaps one day contributing to the emergence of new life. At the center of the remnant, something strange will remain. The core that triggered the explosion does not simply vanish. Instead, it compresses into an incredibly dense object, either a neutron star or possibly a black hole. A neutron star is what you get when you take a mass comparable to the Sun and squeeze it into a sphere just a few miles across. The result is matter so dense that a teaspoon of it would weigh billions of tons. A black hole is even more extreme, a region where gravity has become so strong that nothing, not even light, can escape. Whether Betelgeuse's core becomes a neutron star or a black hole depends on its exact mass, and this is something astronomers still debate. Current estimates suggest that Betelgeuse's core is probably right around the boundary between these two outcomes. When the supernova happens, detailed observations of the explosion and its aftermath will finally settle the question. The story of Betelgeuse from the great dimming to its eventual supernova, reminds us of something profound about our place in the universe. We are intimately connected to the stars, not just poetically, but literally. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were created in the cores of massive stars, like Betelgeuse, and scattered across the cosmos by supernovae that exploded billions of years ago. When you look up at Betelgeuse on a clear night, you are looking at a factory that is even now creating the raw materials of future worlds. The carbon being fused in its core, the oxygen and silicon in its inner shells, all of this will one day be liberated by the supernova and seeded into the galaxy. Perhaps billions of years from now, those atoms will find their way into a new planet, a new ocean, or a new living being that looks up at its own night sky and wonders at the stars. This is the cosmic cycle of matter, and it has been repeating for billions of years. Betelgeuse is not the first red supergiant to light up our sky, and will not be the last, but it is ours to watch, ours to study, and ours to learn from. The Great Dimming gave us a glimpse into the dramatic events that shaped these stellar giants. The eventual supernova will teach us even more. Until that distant day arrives, Betelgeuse continues to burn in Orion's shoulder, a patient reminder that even the brightest stars have stories to tell if we take the time to listen. Let us turn our attention now to the specific telescopes and observations that have helped astronomers unravel the mystery of the Great Dimming. This is a story of international collaboration, cutting-edge technology, and the persistent curiosity that drives scientific discovery. The Hubble Space Telescope played a crucial role in understanding what happened to Betelgeuse. This remarkable observatory has been circling Earth since 1990, peering into the depths of space with unprecedented clarity. Free from the blurring effects of Earth's atmosphere, Hubble can resolve details that ground-based telescopes struggle to see. For a nearby star like Betelgeuse, this means Hubble can actually image the disk of the star itself, rather than seeing it as a mere point of light. In the months surrounding the Great Dimming, Hubble captured a series of images showing changes in the ultraviolet light coming from Betelgeuse's surface. These observations revealed something extraordinary. In September and October of 2019, just before the dimming became severe, Hubble detected an enormous amount of hot material moving outward from the star's surface at tremendous speed. This was the surface mass ejection in action, caught on camera. The Hubble data showed that the ejected material was moving at roughly 200,000 miles per hour. At such speeds, the plume quickly traveled far enough from the star's surface to begin cooling. By November and December, as the material continued to expand and cool, dust particles began forming. By January of 2020, the dust cloud had grown dense enough to significantly block Betelgeuse's light from our perspective here on Earth. What makes the Hubble observations particularly valuable is that they captured the event from beginning to end. We have images from before the surface mass ejection occurred, during the ejection itself, as the dust was forming, and throughout the dimming period. This complete timeline allows astronomers to reconstruct the sequence of events with remarkable precision. But Hubble was not working alone. Ground-based observatories around the world contributed their own essential pieces to the puzzle. The Very Large Telescope, operated by the European Southern Observatory in the Atacama Desert of Chile, provided some of the most detailed images of Betelgeuse's surface ever obtained. The VLT consists of 4 giant telescopes, each with a mirror 8.2 meters across. When used together in a technique called interferometry, These telescopes can achieve the resolving power of a much larger single telescope. Using an instrument called SPHERE, which is specifically designed to image objects very close to bright stars, the VLT team captured images showing the dramatic changes on Betelgeuse's visible surface. Before the dimming, the star appeared roughly circular, with the mottled brightness variations typical of a red supergiant's convective surface. During the deepest phase of the dimming, the southern half of the star had become dramatically darker. The asymmetry was striking. It looked as if someone had painted half the star black. This asymmetric dimming was a crucial clue. If Betelgeuse had been dimming because of some internal process affecting the entire star uniformly, we would expect the dimming to be more or less symmetric across the visible disk. Instead, the concentration of the dimming in the southern hemisphere pointed toward an external cause. Something was blocking our view of part of the star, and that something was the dust cloud created by the surface mass ejection. The VLT observations also helped determine the location and extent of the dust cloud. By comparing images taken at different times, astronomers could track how the obscuring region changed. The dust was clearly moving outward from the star, exactly as the ejection model predicted. The data fit beautifully with the timeline constructed from Hubble observations. Another important contribution came from the Atacama Large Millimeter Array, or ALMA, also located in Chile. ALMA is a collection of 66 radio dishes that work together to observe the universe at millimeter and submillimeter wavelengths. These wavelengths are longer than visible light or infrared, and they are particularly useful for studying coal gas and dust around stars. ALMA observations revealed the distribution of silicon monoxide molecules in the space surrounding Betelgeuse. Silicon monoxide is a key ingredient in the dust formation process. When hot gas cools below a certain temperature, silicon and oxygen atoms combine to form these molecules, which then cluster together into dust grains. By mapping where the silicon monoxide was located, ALMA provided a three-dimensional picture of the dust-forming region around the star. The ALMA data showed a clumpy, irregular distribution of material around Betelgeuse. This matched expectations for a star that has been shedding mass through irregular surface eruptions, rather than a smooth, continuous stellar wind. The observations also confirmed that the region responsible for the Great Dimming was located in a specific part of the circumstellar environment, consistent with the ejection event identified by Hubble and the surface changes seen by the VLT. Spectroscopy provided yet another avenue of investigation. By carefully analyzing the exact wavelengths of light coming from Betelgeuse, astronomers could determine the temperature, composition, and motion of material both on the star's surface and in the surrounding space. The Tillinghast reflector, a shell spectrograph at the Fred Lawrence Whipple Observatory in Arizona, contributed valuable spectroscopic data throughout the dimming event. These spectroscopic observations revealed that Betelgeuse's surface temperature had dropped slightly during the dimming. This was initially puzzling, because a simple dust obscuration should not change the apparent temperature of the star's photosphere. The visible surface layer from which the light we see originates. However, the temperature drop turned out to be a secondary effect related to the star's pulsation cycle. Remember those overlapping pulsation periods we discussed earlier? The shorter 400-day cycle causes Betelgeuse to expand and contract rhythmically. When the star is in its contracted phase, the surface is slightly hotter. When it is expanded, the surface is cooler. The Great Dimming coincided with a contraction phase, which means the surface should have been relatively warm. The fact that astronomers measured a slight cooling suggested that the pulsation pattern had been disrupted, possibly by the same forces that triggered the surface mass ejection. This connection between the surface temperature, the pulsation cycle, and the mass ejection event highlights how interconnected the various processes occurring on and around Betelgeuse really are. Nothing happens in isolation. The convective motions that drive the surface, bubbling, the pulsations that cause the star to breathe, and the mass ejections that create circumstellar dust are all manifestations of a single complex system governed by the fundamental physics of stellar structure. The Japanese Subaru telescope, located atop Mauna Kea in Hawaii, contributed observations in the mid-infrared range. These wavelengths are particularly sensitive to warm dust, making them ideal for tracing the material ejected during the surface mass ejection. The Subaru data showed a significant increase in mid-infrared emission from the region around Betelgeuse during and after the dimming event, consistent with newly formed dust being heated by the star's radiation. Back in space, the Solar Terrestrial Relations Observatory, or STEREO, provided an unexpected bonus. STEREO consists of 2 spacecraft designed to study the Sun from different angles, but in their orbits around the Sun, these spacecraft occasionally have opportunities to observe other celestial objects. During a portion of the Great Dimming Event, one of the STEREO spacecraft had Betelgeuse in its field of view and captured photometric data tracking the star's brightness changes from a perspective slightly different from Earth-based observations. The international nature of this observational campaign cannot be overstated. Astronomers from dozens of countries contributed data, analysis, and theoretical modeling. Papers published in scientific journals listed authors from every continent. This collaborative effort allowed the scientific community to piece together the full picture much more quickly than any single institution could have managed alone. As the data came in and the dust hypothesis gained support, theoretical astrophysicists began developing models to explain exactly how such a massive ejection could occur. These models built on decades of research into the physics of red supergiants. But the Great Dimming provided new constraints and motivations for refining the calculations. One key insight emerged from simulations of convection in supergiant stars. Unlike the relatively orderly convection in smaller stars like the Sun, convection in red supergiants can be chaotic and violent. The giant convection cells on Betelgeuse's surface are not stable structures. They form, grow, and dissipate over timescales of months to years. Sometimes, 2 large convection cells can merge, creating an upwelling of unusual power. Other times, a particularly vigorous cell can punch through the star's atmosphere with enough energy to launch material entirely free of the star's gravitational influence. Computer simulations of these processes showed that surface mass ejections of the magnitude required to explain the Great Dimming are not unprecedented. They are rare events, occurring perhaps once every few decades or centuries, but they are a natural consequence of the extreme conditions in red supergiant atmospheres. The simulations also predicted many of the features observed during the event, including the asymmetric nature of the dimming and the timescale over which the dust formed and dispersed. The theoretical work also helped clarify something important about the relationship between the Great Dimming and Betelgeuse's eventual supernova. While surface mass ejections and core collapse are both natural parts of a massive star's life cycle, they occur through entirely different physical mechanisms. The surface mass ejection was a phenomenon involving the star's outer layers and atmosphere. The supernova will be triggered by events in the very core, far removed from the surface processes we can observe. This does not mean there is no connection at all. As massive stars evolve toward their final fate, the conditions in their interiors become increasingly extreme. These extreme conditions can propagate outward, affecting the stability and behavior of the outer layers. Some theorists have suggested that red supergiants might become more prone to dramatic surface events as they approach the end of their lives. But even if this is true, we cannot use surface behavior to reliably predict when the core will collapse. The connection is too indirect, and the core processes remain hidden from view. Let us pause here to appreciate something remarkable about this entire investigation. Betelgeuse is 650 light-years away. That is an almost incomprehensible distance. Light, the fastest thing in the universe, takes more than 6 centuries to bridge the gap between Betelgeuse and Earth. And yet, using nothing but the faint light that reaches our telescopes, astronomers were able to determine that a star had sneezed, figure out when and where on the star's surface the sneeze occurred, measure how fast the ejected material was moving, track the formation of dust particles too small to see with any microscope, and understand how this event affected the star's subsequent behavior. This is the power of modern astrophysics. We cannot touch the stars. We cannot send probes to study them up close. We have nothing but the electromagnetic radiation that travels across the void to tell us their stories. And yet, by carefully analyzing this radiation across the full spectrum from radio waves to gamma rays, we can reconstruct events in astonishing detail. The Great Dimming is a testament to human ingenuity and our relentless drive to understand the universe we inhabit. Now let us look forward and consider what comes next for Betelgeuse and for our study of this remarkable star. In the years since the Great Dimming, astronomers have continued to monitor Betelgeuse closely. The star has gradually brightened again, though its behavior has not fully returned to the pre-dimming baseline. The pulsation cycles that had been tracked for decades appear to have been disrupted. New patterns are emerging, but it will take years of careful observation to fully characterize them. Some researchers have reported what they describe as lingering effects from the surface mass ejection. The star's brightness has shown unusual fluctuations that do not fit neatly into the previously established periodic patterns. The surface temperature has varied in unexpected ways. Even the apparent shape of the star, as measured by interferometric observations, has shown deviations from the pre-dimming norms. These ongoing changes provide continuing opportunities for scientific investigation. Every new observation adds to our understanding of how red supergiants recover from major disruptions. The data will feed into improved theoretical models that can be applied not just to Betelgeuse, but to the broader class of massive stars approaching the end of their lives. One particularly intriguing line of research involves searching for signs that the surface mass ejection may have permanently altered Betelgeuse's mass loss rate. Red supergiants like Betelgeuse are continuously shedding mass through stellar winds. This mass loss affects the star's evolution and influences the eventual supernova. If the Great Dimming event significantly changed the rate at which Betelgeuse loses mass, this could have implications for how the star evolves in the coming millennia. Measuring stellar mass loss is notoriously difficult. The material flowing outward from the star is spread over enormous volumes and is often quite tenuous. But the clues are there for patient observers. Studies of the circumstellar dust, the molecular gas surrounding the star, and the interaction between Betelgeuse's stellar wind and the surrounding interstellar medium can all provide constraints on the mass loss rate. Comparing measurements from before and after the Great Dimming will eventually reveal whether the event had lasting consequences. Another exciting development is the application of asteroseismology to Betelgeuse. Astroseismology is the study of oscillations in stars, analogous to how geologists use seismic waves to study Earth's interior. By analyzing the specific frequencies at which a star pulsates, astronomers can infer properties of its internal structure. For most stars, astroseismology requires extremely precise brightness measurements that can detect tiny oscillations. But Betelgeuse pulsates with such large amplitude that its oscillations are easy to observe. The challenge lies in disentangling the multiple overlapping modes and understanding how they have changed since the Great Dimming. Initial astroseismological analyses suggest that the surface mass ejection may have temporarily dampened certain oscillation modes while exciting others. If confirmed, this would provide a unique window into the connection between surface events and the star's deep interior. No other star has offered such an opportunity for study. Betelgeuse, by virtue of its proximity and its dramatic behavior, has become a natural laboratory for understanding the physics of massive stellar evolution. The James Webb Space Telescope, which began scientific operations in 2022, offers new possibilities for studying Betelgeuse. Webb's infrared capabilities are ideally suited for observing the cool dust and gas around evolved stars. Observations of Betelgeuse by Webb could reveal new details about the structure of the circumstellar environment, the composition of the dust grains formed in the surface mass ejection, and possibly even evidence of previous mass loss events that left their mark in the surrounding material. Webb's sensitivity in the mid-infrared is particularly exciting. This is the wavelength range where cool dust emits most strongly. Previous observations in this range from ground-based telescopes and the Spitzer Space Telescope provided important insights, but Webb's larger mirror and more advanced instruments can see fainter details. The possibility of mapping the three-dimensional distribution of material around Betelgeuse in unprecedented detail is tantalizing. Looking further into the future, astronomers eagerly anticipate observations from the next generation of extremely large ground-based telescopes currently under construction. The Extremely Large Telescope, being built by the European Southern Observatory in Chile, will have a primary mirror 39 meters across, nearly 5 times the diameter of the VLT's individual mirrors. The Giant Magellan Telescope and the 30-meter telescope, both under construction in the Americas, will offer similar revolutionary capabilities. These new telescopes will be able to resolve the surface of Betelgeuse in extraordinary detail. Individual convection cells will be visible. We might be able to watch the formation of a surface mass ejection in real time, rather than reconstructing the event after the fact. The dynamics of the star's atmosphere, currently understood only through models and indirect inferences, will become directly observable. Perhaps most importantly, these powerful new instruments will help astronomers identify the subtle signs that might precede a supernova. While no reliable supernova predictor currently exists, we have limited data to work with. There have been only a handful of observed supernovae in relatively nearby galaxies, and even fewer from which we had pre-explosion observations of the progenitor star. If astronomers catch the right red supergiant at the right time, detailed observations in the years, months, or weeks before explosion could reveal warning signs that would otherwise be missed. Betelgeuse may or may not be that star. The odds of it exploding while the next generation of telescopes is operational are small. But every observation of Betelgeuse and other red supergiants contributes to the baseline of knowledge that will someday allow us to identify a pre-supernova star. When that moment comes, it will revolutionize our understanding of how massive stars end their lives. Let us now turn our attention to the broader context of red supergiants in the cosmos. Betelgeuse is the most famous member of this class of stars, but it is far from unique. Understanding where Betelgeuse fits in the larger population of massive evolved stars helps us appreciate both its significance and its typicality. Red supergiants form from the most massive stars in the universe. When a star is born with more than about 8 times the mass of the Sun, its fate is sealed. It will never fade gently into a white dwarf like our Sun eventually will. Instead, it is destined to blaze through its life in a few million years and end in a catastrophic supernova explosion. Along the way, it will pass through the red supergiant phase, swelling to enormous size and shedding material into space. Not all red supergiants are as massive or as luminous as Betelgeuse. The category encompasses a range of stars with initial masses from roughly 8 to perhaps 40 times the Sun's mass. The most massive stars in this range do not actually become red supergiants. Instead, they lose so much mass through powerful stellar winds that they evolve into Wolf-Rayet stars, hot compact objects very different from Betelgeuse. It is the moderately massive stars, those around 10 to 20 solar masses, that become the classic red supergiants we recognize. Betelgeuse sits comfortably in this range. Estimates of its initial mass cluster around 15 to 20 times the Sun. This makes it a fairly representative example of the red supergiant population. When we study Betelgeuse, we are learning about processes that occur in thousands of similar stars throughout our galaxy. Other prominent red supergiants in the night sky include Antares, the heart of Scorpius, and Mu Cephei, sometimes called Herschel's garnet star for its striking red color. These stars share many properties with Betelgeuse, but differ in the details of their size, luminosity, and evolutionary state. Antares is slightly smaller and cooler than Betelgeuse. Mu Cephei is one of the largest stars known, possibly even larger than Betelgeuse, though accurate size measurements are difficult at its greater distance. Comparing observations of these different red supergiants helps astronomers understand which features are universal to the class and which are specific to individual stars. The giant convection cells, for instance, appear to be a general feature of all red supergiants. They are a natural consequence of the extreme density contrast between the core and the tenuous outer atmosphere. Mass loss through stellar winds is also universal, though the rate varies significantly depending on the star's luminosity and other properties. The surface mass ejections that cause Betelgeuse's great dimming might also be a common phenomenon among red supergiants. Before 2019, we had limited evidence for such events. The great dimming alerted astronomers to the possibility, and subsequent searches have found hints of similar events in other evolved massive stars. As monitoring programs expand and sensitivity improves, we may find that episodic mass ejections are actually quite frequent in the red supergiant population. This has implications beyond astrophysics. The material ejected by red supergiants, whether through steady stellar winds or dramatic surface mass ejections, enriches the interstellar medium with heavy elements. These elements, formed by nuclear fusion in the star's core and dredged up to the surface by convection, become the raw materials for new generations of stars and planets. Understanding the mass loss history of red supergiants is essential for understanding the chemical evolution of galaxies. The dust grains formed in the outflows from red supergiants are particularly important. These tiny particles serve as condensation nuclei in the cool regions of interstellar space. When a new star begins to form, these dust grains help the collapsing gas cloud cool and fragment, influencing the mass distribution of newly formed stars. When planets form around those stars, the dust contributes material to the rocky worlds and asteroids. A direct line of causation connects the dust sneeze that cause Betelgeuse's great dimming to the eventual formation of planets and potentially life in some distant corner of the galaxy. Betelgeuse also plays a role in our understanding of the cosmic distance ladder. Measuring distances to astronomical objects is one of the fundamental challenges of observational astronomy. Various techniques work at different distance scales, and calibrating these techniques requires overlapping measurements of the same objects. Red supergiants like Betelgeuse are bright enough to be seen at tremendous distances. If we can accurately determine the distance to nearby red supergiants using geometric methods, we can calibrate the relationship between their intrinsic brightness and observable properties. This calibration can then be applied to more distant red supergiants in other galaxies, extending the distance ladder further into the cosmos. The distance to Betelgeuse has been measured by several methods, with results generally clustering around 650 light-years. However, there is some uncertainty in this value, and the Great Dimming event has prompted renewed efforts to pin down the distance more precisely. The Gaia Space Telescope, which is measuring positions and distances for over 1 billion stars in our galaxy, has contributed data on Betelgeuse, though the star's extreme brightness and variability complicate the measurements. Future observations should help reduce the uncertainty. Accurately knowing Betelgeuse's distance is important for several reasons. The distance determines our estimates of the star's physical size and luminosity. A different distance would change our understanding of where Betelgeuse sits in its evolutionary sequence and when it might be expected to explode. Resolving the remaining distance uncertainty is an ongoing research priority. As we contemplate the distant future of Betelgeuse, let us also reflect on what this star teaches us about our own cosmic origins. Every atom of oxygen in your lungs traces its history back to a star. Not to a star like our Sun, which will never be hot enough to fuse hydrogen all the way to oxygen, but to a massive star that burned hot and bright and died young. Perhaps that star was a red supergiant like Betelgeuse. Perhaps it existed in this same region of the galaxy, long before our Sun and solar system formed. Perhaps the very oxygen atoms you are breathing right now were once part of a stellar atmosphere, ejected in a mass loss episode or scattered by a supernova explosion. The same story applies to carbon, to nitrogen, to the phosphorus in your DNA, and the iron in your hemoglobin. These elements do not exist naturally in a primordial universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else, the entire periodic table of heavier elements that makes complex chemistry and biology possible, was forged in the hearts of stars and distributed throughout the cosmos by their deaths. This realization, first understood in the middle of the 20th century, has profound implications for how we view ourselves and our place in the universe. We are not separate from the stars. We are made of the stars. The calcium that strengthens your bones came from a supernova. The gold in a wedding ring was likely created in the collision of two neutron stars, the compact remnants of ancient supernovae. The air you breathe, the water you drink, the ground you walk on, all of it connects you to stellar processes that occurred billions of years ago in distant parts of the galaxy. Betelgeuse represents this cosmic cycle in vivid, visible form. Here is a star actively engaged in the process of creating and distributing the elements necessary for worlds and life. The dust cloud that caused the Great Dimming contains silicon, carbon, and oxygen, the building blocks of rocky planets. When Betelgeuse eventually explodes, it will release even more complex elements, along with the energy to drive their dispersal across light years of space. Watching Betelgeuse is like watching the future being written. Somewhere in the galaxy, millions of years from now, a planet might form from material that once resided in Betelgeuse's core. Life might arise on that planet, look up at its own night sky, and wonder about the stars. The connection between us and them, between the past and the future, runs through stars like Betelgeuse, cosmic factories working tirelessly to transform simple hydrogen into the rich tapestry of elements that makes existence as we know it possible. As we approach the end of our journey tonight, let us return one more time to that striking red star on Orion's shoulder. The great dimming is over now. Betelgeuse has brightened again, though it still shows the scars of its cosmic sneeze. The constellation looks normal to casual observers, the familiar hunter with his belt and sword unchanged across the generations. But we know more than our ancestors did. We know that Betelgeuse is not a simple point of light, but a turbulent, dynamic world larger than the orbit of Mars. We know its surface roils with giant convection cells, each one a bubbling cauldron of plasma hotter than any earthly fire. We know that it pulses and breathes, expanding and contracting on timescales we can measure. We know that it sheds material into space, slowly at some times and dramatically at others, contributing to the cosmic cycle of matter that gave rise to our own existence. And we know with certainty that one day Betelgeuse will die in a spectacular explosion that will briefly outshine all the other stars in the sky. When that moment comes, whether in 1,000 years or 100,000, it will mark the end of one star's journey and the beginning of countless others. The elements forged in Betelgeuse will spread throughout this region of the galaxy, waiting for the gravity of new nebulae to gather them, compress them, and ignite new stars. This cycle of stellar birth, death, and rebirth is one of the most beautiful concepts in all of science. It connects us to the universe in ways that our ancestors could never have imagined. When they looked up at Betelgeuse, they saw a mysterious red light, perhaps the eye of a giant, or the marking of a celestial hunter. When we look up at the same star, we see a physical system governed by the same laws of nature that operate here on Earth, a system that is actively participating in the creation of the future. Understanding this connection requires no special equipment. On any clear winter night, you can step outside and find Orion in the eastern sky during evening hours or high overhead, later at night. The 3 belt stars are usually the easiest to spot first. From there, trace up and to the left to find the reddish glow of Betelgeuse. And as you stand there breathing the oxygen made in stars, built from carbon forged in stellar cores, know that you are looking at a factory still at work, a furnace still burning, a giant nearing the end of its grand performance, but not quite finished yet. Let us explore more deeply the physical processes that govern how Betelgeuse and stars like it function. This will help us appreciate both the normalcy of the great dimming and the inevitability of the eventual supernova. At the heart of every star is the process of nuclear fusion. Fusion occurs when atomic nuclei are forced close enough together to overcome their natural electrical repulsion and merge into heavier nuclei. This process releases energy because the resulting heavier nucleus has slightly less mass than the original components. The missing mass is converted into energy according to Einstein's famous equation relating energy and mass. In the core of the Sun, the temperature and pressure are high enough to fuse hydrogen nuclei into helium. This process actually occurs through a series of steps called the proton-proton chain. two protons fuse to form a deuterium nucleus, releasing a positron and a neutrino. The deuterium then captures another proton to form helium-3, and two helium-3 nuclei combine to form helium-4, releasing two protons in the process. The net result is that 4 hydrogen nuclei become one helium nucleus, with the release of energy. Our Sun has been performing this basic trick for about 4.6 billion years, and will continue for another 5 billion or so. But Betelgeuse burned through its hydrogen much faster. More massive stars have higher core temperatures, which dramatically accelerates the fusion rate. A star with 15 times the Sun's mass might burn through its hydrogen in only 10 million years, 1,000 times faster than the Sun. When the hydrogen in the core is exhausted, the core no longer produces the energy needed to support the overlying layers against gravity. The core contracts, and as it does, it heats up. Eventually, it becomes hot enough to fuse helium into carbon through a process called the triple alpha process. 3 helium nuclei, also called alpha particles, combine to form a carbon nucleus. This helium fusion phase is shorter than the hydrogen fusion phase. For a star like Betelgeuse, it might last only 1 million years or so. When the helium runs out, the core contracts again, heats up further, and begins fusing carbon. Carbon burning produces oxygen and neon. Neon burning produces more oxygen and magnesium. Oxygen burning produces silicon and sulfur. And silicon burning produces iron. Each successive phase of fusion is shorter than the one before. While hydrogen burning might last 10 million years, and helium burning 1 million years, carbon burning takes only a few thousand years. Neon burning lasts about a year. Oxygen burning takes a few months. And silicon burning, the final stage, takes only about a day. Yes, a single day. In the final day of a massive star's life, the silicon in its core is rapidly converted into iron. Iron is the end of the line for fusion. Fusing iron nuclei does not release energy. Instead, it requires energy. This means that when the core becomes pure iron, fusion can no longer support the star against gravity. The core collapses and a supernova ensues. We do not know exactly where Betelgeuse is in this sequence. Determining the internal structure of a star from external observations is extraordinarily difficult. Based on its observed properties, estimates suggest that Betelgeuse has probably completed hydrogen and helium burning and is now in the carbon burning phase, or perhaps even more advanced. But there is significant uncertainty. The star might have anywhere from a few thousand to 100,000 years left before the final collapse. This uncertainty is frustrating for those hoping to witness the supernova in their lifetimes. But it is also a reminder of how much we still have to learn. Every observation of Betelgeuse constrains our models just a little bit more. Over time, as our understanding improves, we may be able to narrow down the estimates. For now, we watch and wait and learn. The structure of Betelgeuse resembles an onion, with distinct layers of different composition. At the very center, an inert iron core may already be growing, though this is uncertain. Surrounding the core is a shell where silicon is actively fusing into iron. Outside that is a shell where oxygen is fusing into silicon. Then comes a neon-burning shell, a carbon-burning shell, a helium-burning shell, and finally the vast hydrogen-rich envelope that makes up most of the star's volume. This layered structure is sometimes called an onion shell burning model. Each shell is separated from the next by relatively sharp transitions in composition and temperature. Energy produced in each shell makes its way outward through the overlying material, eventually reaching the surface and radiating into space as the light we observe. The energy transport through the outer layers of Betelgeuse is dominated by convection rather than radiation. In smaller stars like the Sun, energy in the deep interior is carried outward primarily by photons, particles of light that bounce around among the atoms in a slow, random walk toward the surface. Only in the outer layers does convection take over. But in red supergiants, the entire envelope beyond the core is convective. Great currents of hot material rise from the interior, cool at the surface, and sink back down in a continuous churning motion. This global convection explains many of Betelgeuse's observed properties. The rising and sinking motions create the large cells visible on the star's surface. They also dredge up material from deeper layers, bringing products of nuclear fusion to the surface, where they can be detected spectroscopically. And the vigorous motions provide the energy that can occasionally launch material entirely free of the star, as happened in the surface mass ejection responsible for the Great Dimming. The convective envelope of Betelgeuse is so large and so loosely bound by gravity that the star's outer boundary is somewhat fuzzy. Unlike the Sun, which has a relatively well-defined surface called the photosphere, Betelgeuse blends gradually into the surrounding space. The density drops smoothly, rather than ending abruptly. This makes measuring the star's size somewhat ambiguous, and different observations give different results depending on what wavelength of light is used and how the measurement is defined. Despite this fuzziness, we can say with confidence that Betelgeuse is enormously larger than our Sun. If Betelgeuse were placed at the center of our solar system, its outer atmosphere would extend beyond the orbit of Mars. Mercury, Venus, Earth, and Mars would all be engulfed within the star. Jupiter might be just outside or just inside the outermost layers, depending on how you define the edge. This immense size comes with a correspondingly low density. The average density of Betelgeuse is millions of times lower than the average density of the Sun. The outer layers are so tenuous that they would qualify as a decent laboratory vacuum by terrestrial standards. This low density is partly why mass ejections can occur. Material in the outer layers is held only weakly by gravity and can be pushed away by relatively modest forces. The color of Betelgeuse tells us about the temperature of its visible surface. Hotter objects glow blue-white, while cooler objects glow red or orange. The reddish hue of Betelgeuse indicates a surface temperature of about 3,500 Kelvin, or roughly 5,800 degrees Fahrenheit. This is hot by everyday standards, but cool for a star. Our Sun's surface is about 5,800 Kelvin, nearly twice as hot as Betelgeuse's. You might wonder how Betelgeuse can be so luminous if its surface is cooler than the Sun's. The answer lies in its size. The total light output of a star depends on both the temperature of its surface and the surface area. A cooler surface radiates less light per unit area, but if the surface area is enormous, the total output can still be tremendous. Betelgeuse's surface area is perhaps 100 million times greater than the Sun's. Despite being cooler, its total luminosity is about 100,000 times greater. This high luminosity has consequences for the surrounding space. The light pouring out of Betelgeuse exerts pressure on any material in its vicinity. This radiation pressure can push dust grains and gas molecules away from the star, contributing to mass loss even apart from the convection-driven ejections. The steady pressure of light against the particles surrounding Betelgeuse helps drive a continuous stellar wind that carries material outward into interstellar space. The interaction between radiation pressure and circumstellar dust creates some beautiful structures visible in infrared observations. Multiple shells and arcs of material surround Betelgeuse at various distances, marking the locations where successive episodes of mass loss have traveled during their outward journey. These shells provide a historical record of Betelgeuse's past activity, allowing astronomers to estimate mass loss rates over thousands of years. The largest detected shell around Betelgeuse lies about 4 light-years from the star. This material was ejected perhaps 10,000 years ago, during a previous era of enhanced mass loss. The shell is now ploughing into the ambient interstellar medium, creating a bow shock similar to the bow wave in front of a moving ship. This bow shock shows up in infrared images as an arc of emission on one side of Betelgeuse, marking the direction of the star's motion through space. Betelgeuse is indeed moving through the galaxy, like all stars. Its space velocity carries it roughly perpendicular to our line of sight at about 30 kilometers per second relative to the local interstellar medium. Over thousands of years, this motion carries the star and its surrounding envelope through the ambient gas and dust that fills interstellar space. The interactions between the stellar wind and this interstellar medium create the arc-like structures observed around the star. Let us now consider the eventual supernova from a different angle. What will happen to Orion the Hunter when Betelgeuse explodes? Orion is one of the most recognized constellations in the sky, visible from nearly every inhabited part of Earth. The pattern of stars has remained essentially unchanged for thousands of years, providing a fixed reference for navigation, storytelling, and seasonal marking. Ancient Egyptians associated Orion with Osiris. Greeks saw a mighty hunter. Indigenous peoples around the world created their own rich mythologies around this prominent star pattern. When Betelgeuse explodes, Orion will lose its right shoulder. The balanced appearance of the constellation, with Betelgeuse in one corner and Rigel in another, will be disrupted. For weeks or months, the supernova will outshine everything else in Orion, making the familiar pattern unrecognizable. Then, as the supernova fades, observers will notice that something is missing. Where Betelgeuse once glowed, there will be nothing visible to the naked eye. Over time, the supernova remnant will expand and become visible to telescopes as a glowing cloud of gas. This nebula will slowly enlarge over centuries and millennia, eventually spanning an area of sky larger than the full moon. Advanced civilizations thousands of years in our future might see this glowing remnant as a beautiful celestial decoration, a cosmic flower blooming where a great star once stood. The constellation patterns we know are not permanent. They are snapshots of stellar positions at a particular moment in cosmic time. Over millions of years, the motions of individual stars carry them across the sky, gradually dissolving the familiar shapes. In just 100,000 years, the Big Dipper will be unrecognizable. In 1,000,000 years, most of the constellations will have changed beyond recognition. So even without a supernova, Orion would eventually dissolve as its constituent stars drift apart on their separate journeys through the galaxy. The supernova of Betelgeuse will simply accelerate this process for one particular star, removing it from the pattern in a dramatic fashion, rather than letting it slowly drift away. Some people find this impermanence disturbing. The constellations seem eternal, fixed markers in a changing world. Learning that they are actually temporary arrangements of independently moving objects can feel like losing something precious. But there is also beauty in the dynamism. The night sky is not a painted ceiling, but a living three-dimensional space filled with objects on their own journeys. The stars we see tonight are different from the stars ancient people saw, and future generations will see different stars still. Betelgeuse itself is relatively young by stellar standards, having formed only about 8 to 10 million years ago. This means it did not exist when the dinosaurs roamed Earth. When Tyrannosaurus rex looked up at the night sky, Betelgeuse was not there. The star condensed from a cloud of gas and dust sometime around the late Miocene epoch, when our distant ape ancestors were just beginning to walk upright on the African savanna. In cosmic terms, Betelgeuse is practically a newcomer. The cloud from which Betelgeuse formed was itself enriched with heavy elements from previous generations of stars. This is always the case. Every new star contains material that was processed through earlier stellar generations. The first stars in the universe, which formed from the pristine hydrogen and helium of the Big Bang, had no heavy elements at all. These primordial stars lived, died, and scattered their fusion products into space. The next generation formed from this enriched material and further processed it. Each generation adds more complexity to the cosmic inventory of elements. Betelgeuse represents perhaps the third or fourth generation of stars in this region of the galaxy. The carbon, nitrogen, and oxygen in its outer layers were made by stars that lived and died long ago. When Betelgeuse explodes, its own contribution will join this heritage, ready to be incorporated into future stars and planets. This multi-generational aspect of stellar nucleosynthesis is profound. We are not merely made of star stuff. We are made of the accumulated contributions of billions of stars across billions of years. The oxygen you breathe might have been forged in a dozen different stars before arriving on Earth. The iron in your blood passed through multiple stellar generations, each one adding its own transmutations before scattering the enriched material back into space. In this light, Betelgeuse is not an isolated object, but a node in a vast network of cosmic processing that extends across the galaxy and across time. The material entering Betelgeuse came from elsewhere. The material leaving Betelgeuse will go elsewhere. The star is a temporary arrangement, a phase in the endless cycling of matter through stellar furnaces. Let us take a moment to appreciate the tools and techniques that have allowed us to learn so much about Betelgeuse and stars like it. Spectroscopy is perhaps the single most important tool in the astronomer's kit. By spreading starlight into its component wavelengths, spectroscopy reveals the chemical composition, temperature, pressure, velocity, and magnetic properties of distant objects. Almost everything we know about stars beyond basic position and brightness comes from spectroscopic analysis. When Betelgeuse's light passes through a spectrograph, dark lines appear at specific wavelengths. These absorption lines are created when atoms in the star's atmosphere absorb photons of particular energies. Each element produces a unique pattern of lines, a fingerprint that allows identification even across cosmic distances. By analyzing the pattern of lines in Betelgeuse's spectrum, astronomers can determine that its outer layers contain hydrogen, helium, carbon, nitrogen, oxygen, sodium, magnesium, calcium, and many other elements. The detailed shapes of spectral lines carry additional information. If an absorption line appears slightly shifted toward the blue end of the spectrum, it means the material producing that line is moving toward us. A shift toward the red means motion away. These Doppler shifts allow astronomers to measure velocities with remarkable precision. During the surface mass ejection that caused the Great Dimming, spectroscopic observations detected the outward motion of the ejected material, confirming the dust cloud hypothesis. Spectral lines also broaden or narrow depending on temperature and turbulence in the stellar atmosphere. By analyzing line widths, astronomers can infer conditions on the star's surface. The highly turbulent convection on Betelgeuse produces characteristic broadening in its spectral lines, allowing this turbulence to be measured and compared with theoretical models. Interferometry is another powerful technique for studying Betelgeuse. We mentioned earlier that facilities like the VLT can combine light from multiple telescopes to achieve the resolving power of a much larger single telescope. This allows astronomers to directly image the disk of Betelgeuse, rather than seeing it as an unresolved point of light. The basic principle of interferometry is simple. Light waves from a distant object arrive at two separate telescopes. If the object is a point source directly overhead, the waves arrive at both telescopes at the same time and can be combined constructively. But if the object has some finite size or is offset from directly overhead, the waves arrive with a slight time delay between the two telescopes. By measuring how this delay varies as the Earth rotates, astronomers can reconstruct an image of the source. Modern optical interferometers can achieve angular resolutions far better than any single telescope. The Cara array on Mount Wilson in California, for example, can resolve details as small as a few milliarcseconds, roughly equivalent to seeing a quarter from 1,000 miles away. For Betelgeuse, this means we can see features on the star's surface comparable in size to the Earth-Sun distance. Interferometric observations of Betelgeuse over the years have revealed the star to be distinctly non-spherical at times. The giant convection cells create bright and dark patches that give the disk an irregular, lumpy appearance. The pattern changes over months as different cells rise and sink. During the Great Dimming, interferometric observations showed the dramatic asymmetry caused by the obscuring dust cloud. Photometry, the precise measurement of a star's brightness over time, provides yet another window into stellar behavior. By tracking how Betelgeuse's brightness varies, astronomers can identify the pulsation periods that characterize this semi-regular variable star. The historical record of Betelgeuse's brightness extends back over a century, with early visual estimates giving way to increasingly precise electronic measurements. This long baseline of photometric data was essential for recognizing that the Great Dimming was exceptional. Without decades of prior measurements establishing the normal range of Betelgeuse's variability, astronomers might have simply assumed the 2019-2020 faintness was within the usual bounds. The historical record made clear that something unusual was happening. Amateur astronomers play an important role in photometric monitoring of variable stars. Organizations like the American Association of Variable Star Observers coordinate observations from thousands of volunteers around the world, creating continuous records of brightness variations for thousands of stars, including Betelgeuse. During the Great Dimming, amateur observers contributed crucial data that complemented professional observations. These techniques of spectroscopy, interferometry, and photometry, along with many others, form the foundation of observational stellar astrophysics. When combined with theoretical models based on the laws of physics, they allow us to understand objects billions of miles away as thoroughly as we understand processes in our own laboratories. The field of stellar astrophysics has come remarkably far in a relatively short time. A century ago, scientists were still debating what powered the sun. The answer, nuclear fusion, was not firmly established until the late 1930s. The detailed theory of stellar evolution, explaining how stars change over their lifetimes, was not worked out until the 1950s and 1960s. Our understanding of supernovae has advanced dramatically just in recent decades as both theoretical models and observational capabilities have improved. Betelgeuse has been part of this scientific journey from the beginning. It was one of the first stars to have its size measured directly. Back in 1920, using an early form of interferometry. It has been a touchstone for theories of stellar evolution, testing our models of how massive stars behave in their final stages. And the Great Dimming has opened new chapters in our understanding of mass loss and surface dynamics in red supergiants. Future generations of astronomers will continue this work, using tools we cannot yet imagine to ask questions we have not yet thought to pose. Betelgeuse will remain a subject of study as long as it shines, and its eventual supernova will provide a scientific bonanza that researchers will analyze for decades afterward. For now, we have the privilege of watching this cosmic drama unfold in real time. Every night that Betelgeuse appears in the sky, it presents us with new photons carrying information about the star's current state. These photons have traveled for more than 6 centuries to reach us, bringing news of events that occurred when medieval cathedrals were still under construction. By collecting and analyzing this ancient light, we learn secrets of stellar physics that illuminate the workings of the entire cosmos. The question of when Betelgeuse will explode continues to fascinate both scientists and the general public. There is something deeply compelling about knowing that a star visible to our naked eyes is a ticking time bomb, destined to end in one of the most powerful explosions in the universe. The fact that we cannot predict the timing, whether it will happen tomorrow or in 100 millennia, adds to the mystique. Part of the public fascination stems from the human relationship with mortality. We are acutely aware that our individual lives are brief, that the world existed before us and will continue after we are gone. A star on the verge of death, ancient by human standards, but young by cosmic ones, serves as a mirror for our own impermanence. When we contemplate Betelgeuse, we contemplate endings and beginnings on a scale that dwarfs our personal concerns, while somehow connecting to them. There is also the sheer spectacle to consider. Humans have never witnessed a supernova close enough to be easily visible during the day. The most recent naked-eye supernova was in 1987 in the Large Magellanic Cloud, a companion galaxy about 168,000 light-years away. It was visible from the southern hemisphere, but appeared only as a faint star, reaching a peak brightness comparable to Polaris. It was scientifically important, but not particularly dramatic to casual observers. Before that, the last supernova visible in our own galaxy occurred in 1604, observed by Johannes Kepler among others. Kepler's supernova was bright enough to be seen during the day for several weeks. Tycho's supernova of 1572 was similarly spectacular. Further back, historical records describe the supernova of 1054, which created the Crab Nebula. Chinese astronomers called it a guest star and reported that it was visible in daylight for 23 days. A Betelgeuse supernova would exceed all of these in apparent brightness because of its relative proximity. At 650 light-years, Betelgeuse is far closer than the 1987 supernova and comparable in distance to the historical events in our own galaxy. Depending on the exact nature of the explosion, it could rival or exceed the brightest supernova ever reliably recorded. Imagine the impact on our culture. For the first time in recorded history, every human being on Earth would witness a celestial event of this magnitude. News coverage would be constant. Astronomers would hold press conferences explaining what was happening. Amateur stargazers would photograph the new star. Children would ask their parents what that bright light in the sky was. Religious leaders might offer interpretations. Artists would paint it. Poets would write about it. The image of a new star in Orion would become one of the iconic moments of our era. Scientists would be equally excited, though for different reasons. A nearby supernova would provide data of unprecedented quality and completeness. We would be able to study the explosion across the entire electromagnetic spectrum, from radio waves to gamma rays. Neutrino detectors would capture particles from the collapsing core. Gravitational wave observatories might detect ripples in spacetime. The light curve, showing how the brightness changes over time, would be measured with precision impossible for more distant events. This wealth of data would test our theories of stellar evolution, core collapse physics, and explosion mechanisms. Current models make specific predictions about what a supernova should look like at various stages. Comparing these predictions to observations of an actual event would reveal where our understanding is correct and where it needs revision. Every discrepancy would be a learning opportunity, a chance to refine our models and deepen our knowledge. The supernova remnant would be studied for centuries. As the expanding cloud of debris cools and interacts with the surrounding interstellar medium, it passes through different phases that are interesting for different reasons. Initially, the material is so hot that it emits X-rays. As it cools, it transitions to optical emission, glowing in the light of hydrogen, oxygen, and other elements. Later still, radio emission from accelerated particles dominates. Each phase reveals different physical processes and different aspects of the explosion. Young supernova remnants are also sites of particle acceleration. The shock waves that propagate through the expanding debris can accelerate charged particles to extremely high energies, making supernova remnants cosmic particle accelerators. Studying a freshly formed remnant from a nearby supernova would improve our understanding of these acceleration mechanisms, which have implications for cosmic ray physics and high-energy astrophysics more broadly. But we should not get too far ahead of ourselves. All of this excitement is contingent on Betelgeuse actually exploding, which could be tens of thousands of years in the future. In the meantime, we have the star as it currently exists, a magnificent red supergiant going about its cosmic business, offering us a window into the physics of massive stellar evolution. Let us turn our attention to the historical observations of Betelgeuse, which provide context for understanding its current behavior. Betelgeuse has been observed since antiquity, though early records naturally lack the precision of modern measurements. The star's distinctive red color made it notable to ancient observers, who incorporated it into their constellation myths and seasonal calendars. However, detailed scientific study only became possible with the development of modern astronomical instruments in the 19th and 20th centuries. One of the earliest systematic observations of Betelgeuse's variability came from the astronomer John Herschel in the 1830s. Herschel noted that the star's brightness seemed to fluctuate over time, though he did not have the instruments to quantify these changes precisely. Over the following decades, other observers confirmed the variability and began trying to characterize its patterns. By the early 20th century, astronomers had established that Betelgeuse was a semi-regular variable, meaning its brightness changes followed patterns that were roughly periodic, but not strictly predictable. The dominant period of about 400 days emerged from careful analysis of many years of observations. The longer period of about 5.9 years was identified later as more data accumulated. The size of Betelgeuse was first measured directly in 1920, using the interferometric technique pioneered by Albert Michelson. By combining light from two widely separated mirrors and observing the interference pattern, Michelson and his colleagues determined that Betelgeuse had an angular diameter of about 0.047 arcseconds. Combined with distance estimates, This implied a physical size hundreds of times larger than the Sun. This measurement was groundbreaking. For the first time, astronomers had directly determined the size of a star other than the Sun. The result confirmed theoretical expectations that red supergiants must be enormous to explain their observed properties. It also demonstrated the power of interferometry as a tool for stellar research, inspiring further development of the technique. Subsequent measurements refined and updated the size determination. Improved interferometric methods, combined with better distance estimates and understanding of the star's pulsation, have produced size measurements ranging from about 700 to over 1,000 times the Sun's diameter, depending on how the edge of the star is defined and what wavelength of light is used. The star's size actually changes as it pulsates, with the diameter varying by perhaps 10 to 15% over the course of a pulsation cycle. Spectroscopic observations throughout the 20th century revealed the chemical composition of Betelgeuse's atmosphere. The presence of molecules like titanium oxide and water vapor, which cannot exist in hotter stellar atmospheres, confirmed the star's relatively cool surface temperature. Absorption lines from various metals provided information about the abundances of different elements. Evidence of ongoing convection appeared in the broadening and shifting of spectral lines. As technology advanced, observations of Betelgeuse expanded beyond visible light to include infrared, radio, and ultraviolet wavelengths. Each part of the spectrum provides different information. Infrared observations are sensitive to the cool dust and gas surrounding the star. Radio observations can trace molecular emission and the interaction between the stellar wind and interstellar medium. Ultraviolet observations probe hot gas in the upper atmosphere and chromosphere. The launch of space-based observatories dramatically improved our ability to observe Betelgeuse at wavelengths blocked by Earth's atmosphere. The Hubble Space Telescope, operating in both visible and ultraviolet light, has provided crucial observations spanning decades. The Spitzer Space Telescope observed the infrared emission from circumstellar dust. More recently, the James Webb Space Telescope has joined the effort with its unparalleled infrared capabilities. All of this historical data provided the baseline against which the Great Dimming was recognized as extraordinary. When Betelgeuse began fading in late 2019, astronomers could compare the new observations to decades of prior measurements. The historical record made clear that this was not a normal fluctuation, but something unprecedented. The post-dimming period has been characterized by continued close monitoring as the star recovers. The pulsation patterns that were disrupted by the surface mass ejection are gradually settling into new rhythms. Whether the star will eventually return to its pre-dimming behavior or establish a new normal remains to be seen. Years of additional observations will be needed to fully characterize the aftermath. One intriguing question is whether the surface mass ejection was a completely random event, or whether it reflects something about Betelgeuse's evolutionary state. Some theorists have suggested that mass loss episodes might become more frequent or more violent as a star approaches the end of its life. If this is true, the Great Dimming might be an early sign of the final stages of evolution. However, without more examples of similar events from Betelgeuse or other red supergiants, this remains speculative. The study of historical supernovae provides some context for thinking about pre-explosion behavior. Astronomers have examined archival images of locations where supernovae later occurred, trying to identify the progenitor stars and characterize their properties before explosion. In a few cases, pre-explosion variability or mass ejection events have been detected, suggesting that some massive stars become unstable shortly before their deaths. The most famous example is the supernova SN 2009 IP, which produced several bright outbursts in the years before the apparent final explosion. Whether SN 2009 IP was a true supernova or an exceptionally energetic stellar eruption remains debated, but the event demonstrated that massive stars can exhibit dramatic behavior in their final years. Whether Betelgeuse is beginning such a sequence of activity, or whether the Great Dimming was an isolated event in an otherwise stable star, cannot be determined from current data. Let us also consider the broader category of red supergiant variability. Betelgeuse is not the only red supergiant that exhibits complex brightness variations. Many stars of this type show similar semi-regular behavior, with multiple overlapping pulsation periods and occasional episodes of unusual activity. By studying the entire population, astronomers can identify which features are universal and which are specific to particular stars. The pulsation of red supergiants is driven by a process called the Kappa mechanism. The name comes from the Greek letter kappa, used to denote opacity in astrophysical equations. Here is how it works. In certain layers of a star, the opacity, the resistance of the material to the passage of light, depends on temperature in a particular way. When the star contracts slightly, these layers heat up, but the increased temperature causes the opacity to increase. Higher opacity traps more radiation, which builds up pressure and pushes the layer back outward. As the layer expands, it cools, the opacity decreases, radiation escapes more easily, and the layer falls back inward. The cycle repeats, creating rhythmic pulsations. In red supergiants, the Kappa mechanism operates in ionization zones where hydrogen and helium are in the process of being ionized. These zones act as valves, trapping and releasing energy in the way just described. The exact frequencies at which the star pulsates depend on the size, mass, and internal structure of the star. Multiple modes can be excited simultaneously, which is why stars like Betelgeuse show several overlapping periods. The pulsations affect not just the brightness, but also the size, surface temperature, and spectral appearance of the star. As Betelgeuse expands, its surface cools and the brightness in certain wavelength bands decreases. As it contracts, the surface heats up and the brightness increases. The detailed relationship between these quantities, carefully measured over many pulsation cycles, provides constraints on theoretical models of stellar structure. Understanding pulsation is important for more than just the individual stars involved. The period luminosity relationship for certain types of pulsating stars, particularly Cepheids, is a cornerstone of the cosmic distance ladder. By establishing similar relationships for red supergiants, astronomers can extend distance measurements to galaxies where these bright stars can be observed but fainter Cepheids cannot. This has practical implications for measuring the expansion rate of the universe and testing cosmological models. Betelgeuse's proximity makes it particularly valuable for calibrating these relationships. If we can precisely determine the distance to Betelgeuse and simultaneously measure its pulsation properties and intrinsic luminosity, we can anchor the red supergiant branch of the distance ladder. This is one reason why improving the distance estimate to Betelgeuse is an ongoing research priority. The Gaia spacecraft has revolutionized stellar distance measurements by using the parallax method with unprecedented precision. Parallax involves measuring the apparent shift in a star's position as Earth moves around the Sun. A star closer to Earth will appear to shift more than a star farther away. By precisely measuring this shift, the distance can be calculated. For most stars, Gaia provides superb parallax measurements. However, Betelgeuse presents special challenges. The star is so bright, that it saturates Gaia's detectors in the normal operating mode. Special procedures are needed to observe such bright stars, and the resulting measurements are less precise than for fainter objects. Additionally, Betelgeuse's large angular size and variable surface brightness complicate the determination of its exact position. Despite these challenges, Gaia has contributed to refined distance estimates for Betelgeuse. Combined with other measurements using different techniques, the current best estimate puts the star at about 650 light-years, with an uncertainty of perhaps 10%. Future observations may narrow this uncertainty, but for now, 650 light-years serves as a reasonable working value. At this distance, light from Betelgeuse takes about 650 years to reach Earth. This means we are seeing the star as it was around the year 1375, not as it is today. The Betelgeuse we observe tonight might already have exploded, with the light from the supernova still racing toward us across the interstellar void. This possibility, while scientifically valid, should not be overemphasized. The probability that Betelgeuse exploded in the last 650 years is small, but it captures the imagination in a way that highlights the strange temporal relationships created by the finite speed of light. Consider an even more dramatic scenario. Suppose Betelgeuse exploded exactly 650 years ago, in the year 1375. The light from that explosion would be arriving at Earth right now. Perhaps tonight, someone will look up at Orion and see not the familiar red glow of Betelgeuse, but the blazing brilliance of a new star. The neutrino burst that precedes the optical display might already be washing through our planet at this very moment, undetected unless it triggers one of our sensitive neutrino observatories. This is almost certainly not happening. The odds are overwhelmingly against such precise timing, but the fact that it could be happening, that at any moment the messenger particles from a stellar catastrophe might arrive without warning, speaks to the dynamic nature of the universe we inhabit. The sky that seems so stable, so reliably the same night after night, could change dramatically at any moment. Neutrino detection offers our best chance of advance warning before a supernova becomes visible. When a massive star's core collapses, the initial event produces an enormous burst of neutrinos. These ghostly particles interact so weakly with matter that they pass directly through the star's outer layers and travel at nearly the speed of light to Earth. The optical display, the brilliant new star that everyone sees, comes later, after the shockwave from the core collapse has propagated through the star and blown it apart. For a star like Betelgeuse, the neutrino burst would arrive several hours to perhaps a day before the optical brightening. Large neutrino detectors around the world, including Super Kamiokande in Japan, IceCube in Antarctica, and others, are constantly watching for exactly this signal. If they detect the characteristic burst pattern from a galactic supernova, automatic alerts are sent to astronomical observatories worldwide. Within minutes, telescopes would be training on Betelgeuse, capturing the first moments of the optical explosion. The detection of neutrinos from supernova 1987A validated this theoretical picture. 25 neutrinos from the explosion were detected by two different experiments, arriving several hours before the optical brightening became apparent. This small handful of particles provided crucial information about the core collapse process, confirming that our theoretical understanding was on the right track. A supernova at Betelgeuse's distance would produce orders of magnitude more detected neutrinos, enabling far more detailed studies. Gravitational wave detection offers another potential window. The core collapse that triggers a supernova involves the rapid motion of tremendous masses under extreme gravitational conditions. This violent event should produce gravitational waves, ripples in the fabric of space-time itself. Current gravitational wave detectors like LIGO and Virgo are sensitive to merging black holes and neutron stars. A galactic supernova might also produce a detectable signal, though the characteristics would be quite different from the binary merger events detected so far. The combination of neutrino, gravitational wave, and electromagnetic observations of a single supernova event would usher in a new era of multi-messenger astronomy. Each messenger carries different information about the underlying physics. Neutrinos tell us about the core, collapse itself. Gravitational waves reveal the dynamics of the collapsing and bouncing core. Electromagnetic radiation across the spectrum shows us the expanding debris and its interaction with surrounding material. Together, they would provide the most complete picture ever obtained of how a massive star ends its life. For all these reasons, astronomers eagerly await the next galactic supernova, whether it comes from Betelgeuse or some other massive star nearing the end of its life. The wait could be short, or it could be long. On average, supernova explosions occur in a galaxy like ours roughly once or twice per century. We are somewhat overdue, but stellar explosions are random events that do not care about averages. The next one could happen tomorrow, or it could be decades away. Betelgeuse is one of the best candidates for the next visible supernova, but it is not the only one. Other red supergiants, including Antares in Scorpius, are also potential progenitors. Some stars that appear less promising at first glance might actually be closer to explosion. The difficulty in predicting supernova timing applies to all massive stars, not just Betelgeuse. In the meantime, we continue to watch and study. Every observation adds to our knowledge. Every measurement refines our models. The stars keep their own timetables, indifferent to our curiosity, but generous with their light. And somewhere out in space, traveling toward us right now, may be the photons or neutrinos or gravitational ripples from an explosion that has already happened but not yet reached us. The universe is full of traveling messages, and we are constantly receiving news from deep in the past. Let us reflect for a while on what Betelgeuse teaches us about our place in the cosmos. This is not merely a scientific exercise, but a philosophical one. The facts we have discussed, the fusion reactions, the convective cells, the mass ejections, and the eventual supernova, all point toward deeper truths about the nature of existence itself. First, there is the matter of scale. Betelgeuse is so large that human intuition struggles to grasp it. We can write down numbers, saying the star is 700 or 800 or 1,000 times the diameter of the Sun. We can state that it would engulf the inner planets of our solar system. But truly comprehending these dimensions is beyond the capabilities of minds evolved to navigate African savannas and hunt medium-sized prey. This failure of intuition is itself instructive. The universe is not built to human scale. Our senses and mental models are adapted to the narrow range of sizes, times, and energies that mattered for our evolutionary survival. Beyond that range, we must rely on mathematics and instruments to explore realities that evolution never prepared us for. Science is, in this sense, a transcendence of our biological limitations. Through careful reasoning and clever experiments, we can understand phenomena that no human will ever directly experience. Second, there is the matter of time. Betelgeuse formed perhaps 10 million years ago, a duration that vastly exceeds the span of human civilization. The light we see tonight left the star around the year 1375, centuries before anyone now alive was born. The supernova, when it comes, might not occur for 100,000 years. long after everyone reading these words has passed away. These timescales humble us. Individual human lives are brief flickers against the cosmic darkness. Even our civilizations, which seem so permanent to those living within them, are transient arrangements that will eventually give way to whatever comes next. Betelgeuse will outlast us, though it too will end. The universe is patient. It was here before us and will continue after we are gone. But there is comfort in this perspective as well. Our atoms were forged in stars like Betelgeuse. The very substance of our bodies is ancient beyond imagining, recycled through cosmic processes countless times before arriving in the forms we now inhabit. When we look at Betelgeuse, we are looking at kin. The carbon in our cells and the carbon in that distant star were made by the same nuclear processes, governed by the same laws of physics. We are not separate from the cosmos, but expressions of it. Third, there is the matter of connection. Every photon that reaches us from Betelgeuse carries information about events occurring hundreds of years ago and hundreds of trillions of miles away. Yet we can capture these photons, analyze them, and reconstruct with remarkable accuracy what is happening on and around a star we will never visit. This connection across space and time is one of the great gifts of the scientific method. We are not isolated on our small planet. Through the light that reaches us, we participate in a cosmic conversation that spans the observable universe. The elements created in Betelgeuse will one day join this conversation more directly. When the star explodes, its enriched material will disperse into interstellar space. Over millions of years, gravity will gather some of this material into new clouds that collapse into new stars with new planetary systems. The oxygen and carbon and silicon forged in Betelgeuse's core may one day become part of an ocean, a tree, or a living being on some world we cannot imagine. This is the cosmic cycle at its most profound. Matter flows from star to star, transformed by nuclear fire, scattered by cosmic explosions, gathered by gravity, and transformed again. The cycle has no beginning we can identify, and no end we can foresee. It simply continues, endlessly creative, endlessly renewing. Let us also consider what it means to be alive at this particular moment in cosmic history. Betelgeuse has been shining for millions of years and will continue for thousands or hundreds of thousands more. Human civilization, in contrast, has existed for only a few thousand years. The overlap between our presence and Betelgeuse's remaining lifetime is a tiny sliver of cosmic time. And yet, within that sliver, we have developed the ability to understand what Betelgeuse is. For most of human history, the red star on Orion's shoulder was simply a mysterious light in the sky. Only in the last century have we come to understand its true nature. A dying giant, burning through the final stages of nuclear fuel, destined for spectacular destruction. We are among the first humans to possess this knowledge. This knowledge is a responsibility, as much as it is a privilege. We are the storytellers of the cosmos, the beings who can look at the stars and comprehend what they are. This capacity for understanding is precious. It should be nurtured and shared. When you next look at Betelgeuse, you might try sharing what you know with someone who has not heard the story. Tell them about the red supergiant, the pulsating giant convection cells, the dust sneeze that cause the great dimming. Explain how the elements in their body were forged in stars like this one. Show them how science has revealed the cosmic cycle that connects us all. Science at its best is not a collection of facts to be memorized, but a way of seeing the world. The story of Betelgeuse illustrates this perfectly. What appears to the casual observer as a simple red star becomes, through scientific investigation, a window into fundamental processes of physics and chemistry. The same light that ancient peoples saw as a marker in their constellation myths now reveals the deepest secrets of stellar evolution. This transformation from mystery to understanding is what science offers. It does not diminish the wonder. If anything, it enhances it. Knowing what Betelgeuse is makes the view more impressive, not less. The mystery does not disappear. It simply becomes more specific. We no longer wonder what that red light is. Now we wonder exactly when the iron core will reach critical mass, precisely how the convection cells give rise to surface mass ejections, and what new physics we might learn when the supernova finally occurs. The journey of discovery continues. Every generation of astronomers learns more about Betelgeuse and stars like it. Future generations will learn still more. Perhaps they will witness the supernova itself, an event that would be simultaneously an ending and a beginning. The death of the star would mark the birth of new understanding, as data from the explosion revolutionizes our models of stellar physics. Those future astronomers will stand on the shoulders of everyone who came before. They will use instruments we cannot imagine to ask questions we have not thought of. But their work will be continuous with ours, part of the same grand project of understanding that began when the first humans looked up at the night sky and wondered. Let us take a moment to simply appreciate the beauty of what we have learned. A star vastly larger than our sun pulsates rhythmically, driven by the physics of opacity and radiation pressure. Giant cells of plasma rise and fall on its surface like bubbles in slowly boiling water. Hot material is expelled into space, cooling into dust clouds that scatter starlight across the cosmos. Deep in the core, nuclear fusion builds an onion-like structure of increasingly heavy elements. The iron ash at the very center grows grain by grain, approaching the critical mass that will trigger catastrophic collapse. All of this happens continuously, right now as you listen to these words, though the light reaching us shows events from centuries ago. The processes are real and ongoing. The star does not pause. The fusion reactions proceed. The convection churns. The stellar wind blows, and inexorably, inevitably, the moment of final collapse approaches. There is a kind of tragedy in this. Betelgeuse is beautiful, and beauty should not have to end. We might wish for the star to shine forever, a permanent fixture in the winter sky. But the laws of physics do not share our preferences. Massive stars burn fast and die young. It is the price of brilliance. Yet the tragedy is not complete. From the death of Betelgeuse, new possibilities will emerge. The scattered elements will find their way into new stars and new worlds. The energy released by the supernova will power chemical reactions across light years. And on some future planet, beings might look up at their sky and wonder about the stars, never knowing that the very atoms of their bodies were once part of a red supergiant that dazzled the skies of an ancient planet called Earth. This is the cosmic promise. Nothing is truly lost. Everything is transformed. The cycle continues. Let us return now to the immediate present and consider what you might do with the knowledge you have gained tonight. The next time Orion rises in the east on a clear winter evening, take a few minutes to find Betelgeuse. Look for the distinctive belt of 3 stars, then trace up and to the left to find the reddish glow. Compare its color to the blue-white sparkle of Rigel on the opposite corner. Notice how the constellation's visual balance depends on both stars. As you stand there, breathe deeply and remember that the oxygen filling your lungs was made in a star. The carbon in the exhaled carbon dioxide was also stellar. You are participating in the cosmic cycle simply by breathing, exchanging atoms with the air, cycling matter through your body, returning it to the environment to be cycled again. Think about the light entering your eyes. Those photons left Betelgeuse around the year 1375 and have been traveling through the void ever since. They have not interacted with anything during their journey. They carry information encoded at the moment of their creation, information that your eyes are now receiving and your brain is processing. You are in communication with a star hundreds of light years away, receiving a message from the medieval past. If the sky is particularly clear and you have been outside long enough for your eyes to adapt to the darkness, you might notice the faint glow of the Milky Way stretching overhead. This is the combined light of hundreds of billions of stars, most of them too far away to see individually. Within that glow are countless red supergiants like Betelgeuse, each one destined for its own spectacular end. The galaxy is peppered with these cosmic time bombs, silently ticking toward explosions that will seed space with the elements of life. Our solar system formed from the debris of such explosions. The very ground you stand on, the planet that hosts all life as we know it, is recycled stardust. You are recycled stardust. The iron in your blood was forged in a stellar core under unimaginable pressure and temperature, then scattered into space by a supernova, then gathered by gravity into a cloud that collapsed into our sun and its planets, then incorporated into the living systems that eventually gave rise to you. This chain of causation connects you directly to the hearts of long-dead stars. There is a meditation in this. When we feel small or insignificant, we might remember that we are literally made of star stuff. Our sense of insignificance comes from comparing ourselves to the vast scales of space and time. But considered from another angle, we are remarkable precisely because we can make that comparison. We are the part of the universe that knows about the rest of it. We are matter aware of itself, stardust contemplating the stars. Betelgeuse does not know it is Betelgeuse. The star has no consciousness, no awareness of its nature or its fate. The plasma churns, the fusion reactions proceed, the physics unfolds according to impersonal laws. But on one small planet orbiting an ordinary star hundreds of light years away, beings have looked at this light and understood what it means. We have named the star. We have measured its properties. We have theorized about its future. We have marveled at its beauty. This capacity for wonder is our great gift. The universe is full of amazing things, but most of it has no one to be amazed. Stars are born and die unwitnessed. Galaxies collide and merge without anyone to record the event. Black holes swallow light, and dark matter sculpts cosmic structure, all without observers. But here on Earth, for this brief moment in cosmic time, there are creatures who can look up and appreciate what they see. This appreciation is worth cultivating. The wonder does not come automatically. It requires some knowledge, some context, some willingness to pause and reflect. When we learn about Betelgeuse, we are not just accumulating facts. We are training ourselves to see more deeply, to appreciate more fully, to connect more meaningfully with the universe that created us. And so we come to the end of our exploration tonight. We have traveled far, from the first glimpse of a dimming star in late 2019 to the fundamental physics of nuclear fusion, from the technical details of interferometric observation to the philosophical implications of cosmic time. Betelgeuse has been our guide throughout, a single star that opens windows onto the entire universe. The story is not finished. Betelgeuse continues to shine. Astronomers continue to watch. New observations will refine our understanding. And someday, perhaps sooner than we expect, or perhaps far in the future, the star will reach the end of its story and begin a new one. When that moment comes, remember what you learned tonight. Remember the great dimming and its cause. Remember the giant convection cells and the surface mass ejections. Remember the onion shell structure and the iron core slowly growing toward its critical mass. Remember that the supernova, when it finally occurs, will scatter elements into space that may one day become parts of new worlds and new beings. And remember that you are part of this story too. The atoms in your body came from stars that lived and died before our sun was born. When you eventually return those atoms to the environment, they will continue the cycle, perhaps one day finding their way into stars yet unborn. You are a temporary arrangement of cosmic matter, briefly self-aware, lucky enough to live in an era when we can understand our place in the grand scheme. Take that understanding and let it enrich your life. Let the vastness of the cosmos put your daily troubles in perspective. Let the beauty of stellar evolution inspire your sense of wonder. Let the long reach of cosmic time remind you that your moment matters precisely because it is fleeting. The night sky is waiting. Betelgeuse is burning. The universe is telling its story, and you are here to listen. Thank you for joining me on this journey tonight. If you enjoyed this exploration, please subscribe to the channel and consider sharing this video with someone who might appreciate it. The more people who learn about the wonders of the cosmos, the richer our collective understanding becomes. Until next time, keep looking up. The stars have stories to tell, and we are fortunate to be able to hear them. Good night, and drift peacefully among the stars. Let us dwell a while longer on the quieter aspects of this cosmic story, the subtle details that often go unmentioned, but that contribute to the full picture of what Betelgeuse represents. Consider, for example, the chemistry occurring in the space immediately surrounding the star. The material expelled from Betelgeuse does not simply disperse into empty vacuum. It enters a region filled with molecules, dust grains, and complex interactions between radiation and matter. This circumstellar environment is a laboratory for astrochemistry, where conditions are right for the formation of molecules that would be impossible to create in any terrestrial laboratory. Water vapor has been detected around Betelgeuse, a molecule familiar to us, but surprising to find so close to a star. The water forms in the cooler outer regions of the stellar wind, where temperatures have dropped enough for hydrogen and oxygen atoms to combine. The presence of water tells us something about the conditions in these regions and provides clues about how molecules might form around other evolved stars. Other molecules detected around Betelgeuse include titanium oxide, silicon monoxide, and various carbon-bearing species. These molecules absorb and emit radiation at specific wavelengths, creating distinctive spectral signatures that astronomers can identify and analyze. By studying these signatures, we learn about the temperatures, densities, and chemical processes occurring in regions we cannot directly image. The dust grains that form in the outflows are themselves complex chemical systems. Each grain is a tiny speck of solid material, perhaps only a fraction of a micrometer across, composed of silicates, carbon compounds, or metallic oxides depending on the conditions of its formation. The surface of each grain provides a site for chemical reactions to occur, reactions that might not happen efficiently in the gas phase alone. These grains are important for more than just their immediate chemistry. They are the seeds from which planets eventually form. In the nebulae that give birth to new stars, dust grains collide and stick together, gradually building larger and larger aggregates. Over millions of years, These aggregates grow into pebbles, then boulders, then planetesimals, and eventually planets. The dust ejected by Betelgeuse and stars, like it, is the raw material for future worlds. The surface of Betelgeuse itself is a fascinating environment, though perhaps not what we usually imagine when we think of a star's surface. Unlike the relatively calm photosphere of the Sun, Betelgeuse's surface is a roiling sea of plasma dominated by enormous convective upwellings. If you could somehow stand on a platform above this surface, you would see a landscape of rising and falling mountains of incandescent gas, each one larger than the orbit of Earth around the Sun. The concept of temperature on such a surface is somewhat complex. Different parts of the surface have different temperatures, depending on whether they correspond to rising hot material or sinking cooler material. The bright spots on Betelgeuse's disk are regions where hot plasma is welling up from below. The darker regions are where cooler material is sinking back down. The overall temperature we assign to the star is an average over these varying conditions. The magnetic field of Betelgeuse is another area of active research. Our Sun has a complex magnetic field that drives solar activity, producing sunspots, flares, and coronal mass ejections. Red supergiants like Betelgeuse also have magnetic fields, though the structure and dynamics of these fields are less well understood. Some researchers have suggested that magnetic activity might play a role in triggering surface mass ejections, though the connection remains speculative. Measuring the magnetic field of a distant star is extremely challenging. The technique relies on detecting the subtle effects that magnetic fields have on spectral lines, causing them to split into multiple components or become polarized in characteristic ways. For a star like Betelgeuse, with its turbulent atmosphere and complex spectral features, disentangling these effects requires careful analysis and sophisticated instruments. Despite these challenges, astronomers have detected evidence of a magnetic field on Betelgeuse. The field appears to be relatively weak compared to what is found on smaller, more active stars, but it may still play an important role in shaping the dynamics of the stellar atmosphere and wind. Future observations with more sensitive instruments may reveal the structure of this field in greater detail. Let us also consider the role that Betelgeuse plays in the broader ecology of the galaxy. We have discussed how the elements created in the star's core will eventually be distributed into space by the supernova explosion. But even now, before the supernova, Betelgeuse is contributing to the chemical enrichment of its surroundings through its ongoing mass loss. The stellar wind carries material outward at speeds of around 10 to 15 kilometers per second. This seems slow compared to the velocities involved in the surface mass ejection, but over millions of years, even a slow wind transports significant amounts of mass. Estimates suggest that Betelgeuse has already lost perhaps a solar mass worth of material through its wind since becoming a red supergiant. This material is now spread across a vast volume of space surrounding the star. The wind interacts with the surrounding interstellar medium, creating the bow shock structure we mentioned earlier. At the boundary, where the wind meets the ambient gas, the collision heats the material and produces emission that can be detected at various wavelengths. By studying this interaction region, astronomers can learn about both the properties of the stellar wind and the conditions in the local interstellar medium. The material lost through the wind is enriched in certain elements compared to the original composition of the star. Convective dredge-up brings products of nuclear fusion from the interior to the surface, where they can be carried away by the wind. This means that Betelgeuse is gradually seeding its surroundings with carbon, nitrogen, and other elements even before the supernova occurs. This pre-supernova enrichment is significant because it prepares the environment for what comes after. The supernova shock wave will sweep up the material previously ejected by the wind, compressing it and triggering new chemical reactions. The interaction between the supernova debris and the wind-blown bubble will shape the structure of the resulting supernova remnant for thousands of years to come. The rate at which Betelgeuse loses mass has implications for when the supernova will occur. More massive stars generally explode sooner than less massive ones, and mass loss reduces the final mass that collapses. If Betelgeuse is losing mass rapidly, it might actually extend its remaining lifetime slightly, since less mass means less rapid burning in the core. However, the effect is probably not large enough to significantly change our estimates of when the supernova might happen. Determining the mass loss rate accurately is one of the ongoing challenges in Betelgeuse research. Different methods give somewhat different answers, and the rate probably varies over time as the star pulsates and undergoes episodic events like the surface mass ejection that cause the great dimming. The best current estimates suggest a mass loss rate of roughly 100,000th of a solar mass per year, but there is significant uncertainty in this number. The question of how much mass Betelgeuse has lost over its lifetime connects to the broader question of how much mass it had when it first formed. This initial mass is important because it determines many aspects of the star's subsequent evolution, including how long each phase lasts and what type of compact remnant will be left after the supernova. Astronomers estimate Betelgeuse's initial mass by comparing its observed properties to theoretical models of stellar evolution. The models predict what a star of a given initial mass should look like at various stages of its life. By finding the model that best matches Betelgeuse's current size, temperature, luminosity, and other properties, researchers can infer what the initial mass must have been. Current estimates cluster around 15 to 20 solar masses for the initial mass, with the star having already lost several solar masses through its winds. This makes Betelgeuse a moderately massive star by red supergiant standards, large enough to end its life as a supernova, but probably not so massive that it will leave behind a black hole rather than a neutron star. The uncertainty in these estimates reflects the limitations of both the observations and the theoretical models. Stellar evolution is a complex process involving many interacting physical phenomena, and our models are necessarily simplified representations of reality. As both observations and models improve, the estimates will become more precise. Let us spend a moment considering what the view might look like from a planet orbiting a red supergiant like Betelgeuse. Such a planet could not exist in the modern era, since any inner planets would have been engulfed when the star expanded. But we can imagine a hypothetical planet at a safe distance and ask what the sky might look like from its surface. The star itself would dominate the sky, appearing as an enormous reddish disk rather than a mere point of light. The disk might subtend angles of many degrees, 100 times larger than the sun appears in our sky. The surface features, the bright and dark patches created by convection, would be visible as distinct regions within the disk. The light bathing such a planet would be predominantly red and infrared. Any life that evolved there would have senses adapted to this wavelength range. Such a planet would also experience dramatic changes as the star pulsated. The size of the stellar disk would grow and shrink by perhaps 10% over the course of a pulsation cycle. Any inhabitants would experience regular cycles of brightness and dimness that would make our seasonal variations seem trivial by comparison. Of course, such a scenario is purely hypothetical. the chances of a planet surviving at the right distance are slim, and conditions would be extremely hostile to life as we understand it. But the exercise of imagination helps us appreciate how different the universe can be from the narrow range of conditions we experience on Earth. Returning to Betelgeuse, let us consider one more aspect of its significance: its role as a calibration object for astronomical instruments. Because Betelgeuse is bright and has well-studied properties, it serves as a reference standard for many types of measurements. Observers testing new instruments often point them at Betelgeuse to verify that they are working correctly. The star's known brightness, spectrum, and angular size provide benchmarks against which instrument performance can be assessed. If a new spectrograph produces results that deviate from expectations for Betelgeuse, the astronomers know they need to investigate whether something is wrong with their equipment or their data reduction procedures. This calibration role extends to amateur astronomers as well. Those learning to use telescopes or to make brightness estimates often practice on Betelgeuse because of its accessibility. The star serves as a training ground for observers at all levels. The historical record of Betelgeuse observations is valuable. More than a century of careful measurements document how the star has behaved over time. This record provides the baseline against which unusual events like the Great Dimming can be recognized and evaluated. Without the patient work of generations of observers, both professional and amateur, we would not have known that the 2019-2020 dimming was exceptional. This brings us to a broader point about astronomical research. Astronomy is a field where patience is essential. The processes we study unfold over timescales that dwarf human lifetimes. Progress often comes not from dramatic discoveries, but from the slow accumulation of data over years and decades. The astronomers who began monitoring Betelgeuse a century ago could not have known that their observations would one day help explain a stellar sneeze that had not yet occurred. They simply did the work because it seemed worth doing, trusting that future generations would find value in their records. This trust across generations is one of the beautiful aspects of science. Each generation builds on the work of those who came before and lays foundations for those who will follow. The story of Betelgeuse is not just a story about a star. It is also a story about human cooperation across time, about the patient accumulation of knowledge, about the faith that understanding is worth pursuing even when the payoff is uncertain. The star will continue to be monitored. New telescopes will provide new data. Future generations of astronomers will refine our understanding of what we have observed. And when the supernova eventually occurs, scientists will look back at all the preceding observations from John Herschel in the 1830s through the Great Dimming of 2019-2020 and use them to understand the full story of how this magnificent star lived and died. Until that day, Betelgeuse keeps shining. The red light travels through space, carrying news of events long past. And somewhere on Earth, someone is looking up at that light and wondering what secrets it might reveal. As we prepare to close this chapter of our cosmic journey, let us take one final moment to appreciate the quiet majesty of what we have explored together. The universe is vast beyond comprehension, filled with wonders that challenge our capacity for understanding. Yet somehow, through the patient work of countless observers over many generations, we have come to know a great deal about even distant objects like Betelgeuse. We know its composition, its structure, its behavior, and its fate. We know that it will one day explode in a supernova that will outshine all the other stars in the galaxy. We know that its scattered remains will contribute to the formation of new stars and new worlds. This knowledge does not diminish the mystery. If anything, it deepens it. Every answer leads to new questions. Every discovery reveals new puzzles to solve. The more we learn about Betelgeuse, the more we realize how much remains unknown about the processes that govern stellar evolution. The Great Dimming of 2019 and 2020 was a reminder that the universe can still surprise us. Even a star that has been observed for centuries can suddenly do something unexpected. The surface mass ejection that caused the dimming was a natural event, consistent with our theoretical understanding, but its magnitude and timing were not predicted. It reminded astronomers that nature always has the capacity to teach us something new. In the years since the Great Dimming, monitoring has continued. Betelgeuse has brightened again and settled into new patterns of behavior. The star is recovering from its cosmic sneeze, adjusting to the loss of material from its outer layers. How long this adjustment will take, and whether the star will eventually return to its pre-dimming behavior or establish a new baseline, remain open questions that only continued observation can answer. The anticipation surrounding Betelgeuse is part of what makes it compelling to study. We know that someday, perhaps in the lifetimes of people alive today, but more likely in the distant future, this star will meet its explosive end. The waiting is itself significant. It reminds us that the universe operates on timescales very different from our own, and that patience is required if we wish to witness its most dramatic events. For those who wish to deepen their connection with Betelgeuse, the path is simple. Go outside on a clear winter night, find Orion, and look at the red star on the hunter's shoulder. No telescope is required. The star is bright enough to see easily with the naked eye. Stand there for a few minutes, letting your eyes adapt to the darkness and your mind drift among the stars. While you stand there, remember what you have learned. Remember that the light reaching your eyes departed more than 6 centuries ago. Remember the giant convection cells churning on that distant surface. Remember the nuclear fires burning in the core, building iron grain by grain toward the critical mass that will trigger collapse. Remember that the very atoms in your body were forged in stars like this one, scattered by ancient supernovae, gathered by gravity, and assembled into the remarkable form that is you. This connection between us and the stars is not poetic metaphor. It is literal truth. We are made of the same stuff as Betelgeuse, governed by the same physical laws, participants in the same cosmic story. When we look at the stars, we are looking at family. When we contemplate their fate, we contemplate our own origins and the origins of everything we know. Sleep well tonight, knowing that the universe continues its ancient processes, whether we watch or not. The stars shine, the elements form. The cycles of creation and destruction proceed across timescales that make human history seem like the blink of an eye. And yet, for this brief moment, we are here to witness it. We are here to understand. We are here to wonder. That is enough. That is more than enough. That is everything.